Hi everyone, I'm Ethan from Microchip Technology. Welcome to part 2 of our Peripheral Touch Controller Deep Dive series. In part 1, we focus on understanding what the Peripheral Touch Controller is, where it's used, and how it works. In this video, we'll apply that knowledge by configuring the Peripheral Touch Controller using Microchip's Code Configurator and Microchip's Touch Library inside of VS Code using the MPLAB extensions. For this example, we'll use the PIC32 CMPL10 Curiosity Nano to configure the Peripheral Touch Controller to detect a press on the onboard capacitive touch button. When pressed, a message is sent over UART and the onboard LED turns on. When released, a corresponding message is sent and the onboard LED turns off. For this demo, we'll use the MPLAB extensions inside of VS Code. If you don't already have VS Code installed, download and install it first. Then, open the extensions marketplace inside of VS Code, search for MPLAB, and install the MPLAB extensions pack. This installs MPLAB tools such as XC compilers, MPLAB Code Configurator, MPLAB Data Visualizer, MPLAB AI Coding Assistant, and any other necessary tools to use MPLAB within VS Code. So, with the extensions installed, the first step is to create a new project. To do this, click on the MPLAB shield icon on the left-hand side. Under the Projects tab, select New Project. Go ahead and give the project a name and keep the default location. Next, select the device that matches the board that you're using. For this example, we're using the PIC32 CMPL10 Curiosity Nano, so we'll select this device here. Then, choose the latest XC32 compiler. Before we move on to the next step, I want to briefly talk about the MPLAB AI Coding Assistant. This assistant is positioned as an expert partner. It's designed to help you develop quicker by answering technical questions, referencing device documentation, and assisting with code for your project. For example, in the context of this video, you could ask, what is the Peripheral Touch Controller? Can you summarize how the Peripheral Touch Controller works? Or show me a block diagram from the datasheet. Because it understands the device that you're using, it can help with peripheral level questions or small code adjustments without you needing to leave your development environment. So with that covered, let's go ahead and keep moving forward. With the MPLAB project created, we can now launch MPLAB Code Configurator, or MCC. For those of you who may not know what MCC is a graphical tool that lets you configure peripherals and system settings through an intuitive interface. It then generates the supporting code based on your setup, so you don't have to manually handle low-level configuration. So to open MCC, use the search window inside of VS Code and type MPLAB MCC launch. When prompted, create a new configuration and proceed with the default MPLAB project settings. Once MCC launches, this is the main screen that we'll be working in today. On the left, you'll see Device Resources and Project Resources. Device Resources lists all the available peripherals and libraries for the device that you're using. Project Resources shows what has already been added to the project. In the center is a project graph, which visually shows the components currently in use. Across the top of the project graph is the plugins menu, where you'll access plugins like pin and clock configuration, and then on the right are the configuration options, where you adjust settings for whichever component is selected. So now that we're familiar with the MCC layout, we can begin adding the peripherals required for this application. Let's start with adding the Peripheral Touch Controller and the Touch Library. In Device Resources, go to Libraries, Harmony, and then expand Touch and add the Touch Library to the project. When added, MCC automatically includes the required dependencies for this touch library, such as the Peripheral Touch Controller and an analog to digital converter, since they work together for capacitive sensing. If the touch library does not appear in your device resources, open the Content Manager, search for Touch, and install the required libraries. Then return to device resources and add it to the project. With the touch library added, we can now configure our touch sensor. To open the touch library, go to the project graph, select Plugins, and choose Touch Configuration. Then, a separate window will open with the Touch Configuration GUI. If this is your first time opening the Touch Library, you'll see a brief walkthrough explaining how the interface is organized and how to navigate the configuration options. Again, since we're using the PIC32 CMPL10 Curiosity Nano, we'll configure the onboard capacitive touch button as our sensor. So the first thing we have to do is select the sensing mode. Because this is a single electrode button, we'll choose self-capacitance. From there, we can set the sensor type to button and configure one button. The touch library also provides options for sliders, wheels, and other sensor types if needed. As sensors are added, the touch library assigns each one as a sequential node index. The first sensor is node 0, and additional sensors increment from there. This index is used in the application code to reference each sensor. With the sensor type configured, now we need to map the sensor to the correct physical pin on the Curiosity Nano. To find this information, open the Curiosity Nano user guide. To do this inside of VS Code, click the MPLAB icon in the sidebar, locate your device under Tools, and click the information icon to open the kit page, which will provide links to documentation of the device that you're using. From there, open the Curiosity Nano user guide and navigate to the pinout section. In the pinout diagram, you'll see the onboard capacitive touch button is connected to PB08 and the shield pin is connected to PB09. The shield pin enables the driven shield feature, which improves touch performance in conditions such as surface moisture. For more information on the driven shield feature, please refer back to part 1 of this video series. Back in the touch configuration window, go to the Configure tab and map button 0 to PB08. Then click on Driven Shield in the right side panel, enable the dedicated shield pin and Driven Shield Plus, and map PB09 as a shield pin. We won't adjust any additional tuning settings in this example, but the other tabs here are where further tuning would be performed if needed. With that, the touch configuration is complete. With the touch configuration complete, next we'll configure the system response to the capacitive button press. First, we'll set up UART communication so the system can send a message to the terminal window whenever the capacitive button state changes. On this device, UART is handled by the SIRCOM modules. Since multiple SIRCOM instances are available, we need to use the one routed to the onboard debugger on the Curiosity Nano. The debugger implements a USB CDC interface, which makes the board appear as a virtual COM port on your PC so we can view UART data in a terminal window. We'll also configure a GPIO to control the onboard LED, giving us visual feedback directly on the board when the capacitive button is pressed or released. So, looking at the Curiosity Nano user guide and the pinout diagram, we can see that SIRCOM 1 is tied to CDC TX and CDC RX, which map to PB00 as pad 0 and PB01 as pad 1 respectively. In the same pinout diagram, we can also see that the onboard LED is connected to PB02. Now that we've identified the correct SIRCOM and pin mapping, let's return to MCC and add and configure them. First, we'll add the SIRCOM module along with standard I/O. SIRCOM 1 handles the actual UART hardware, while standard I/O allows us to use printf to send formatted text over the UART connection. In device resources, navigate to Libraries, Harmony, Peripherals, SIRCOM, and then SIRCOM 1 and add it to the project. Then go to Libraries, Harmony, Tools, Standard I/O, and add standard I/O as well. Once both modules are added, double-click SIRCOM 1 in the project graph to open its configuration window, and then set the operating mode to USART with internal clock, and make sure the baud rate is set to 115200. After that, go back to the project graph and connect the UART node from the SIRCOM 1 block to the UART node on the standard I/O block. Again, what this does, it's going to go ahead and link the UART hardware to standard I/O so printf messages can be routed to the terminal. So with touch, SIRCOM, and standard I/O added and connected, that completes our MCC peripheral setup. The next step is to configure the required pins for our project. In the project graph, select Plugins and open the Pin Configuration plugin. This opens a separate window for managing all pin assignments. You'll see 3 tabs that provide different ways to configure the pins, but for this video, we'll use the Pin Settings tab to manually assign the required functions for each of the pins. Using the pins we identified earlier in the Curiosity Nano user guide, we can now assign them in the Pin Settings tab. First, let's scroll down to pin PB00, open the function dropdown, and select SIRCOM 1, pad 0. Then, let's go to pin PB01 and set its function to SIRCOM 1, pad 1. Next, let's configure the onboard LED. Let's locate pin PB02 and set the function to GPIO and change the direction to out since this will drive our onboard LED. Then, let's assign it the custom name of LED0 so it's easy to reference in the application code. With that, the pin and peripheral configuration for this example is complete. At this point, no more configuration is required, so we can go back to the main MCC window and click the Generate button to create the initialization code and driver APIs. It then generates the supporting code based on your setup, so you don't have to manually handle low-level configuration. So with all the MCC code generated, we can now focus on the application behavior inside of our main. The touch response logic is implemented inside of a function called application_touch processing. At a high level, this function checks whether a touch measurement cycle has completed, reads the sensor state, and then responds by controlling the LED and sending messages to the terminal over UART. I also want to note, MCC also generates supporting files such as touch_example.c and touch_example.h, which were used as reference when structuring this function. That way we don't have to build this function from the ground up. In the main loop, we continuously call touch_process, which is an MCC generated function, and that runs the touch sensing engine and keeps the sensor active. And that's it for our main application code. If you'd like to explore the touch-related functions in more detail, the full source code for this example is available in the project link below. With everything configured and application code written, we're ready to build and program our hardware. In the MPLAB window on the left sidebar, go to the Projects tab and click the hammer icon to clean and build the project. This compiles the code and generates the output file. Once the clean and build completes, click the bug icon to start a debug session and then select the hardware you are using. After the debugger launches, we can press play to run the application code on the Curiosity Nano. At this point, the device is programmed and running our application code. So now we can open a serial terminal to observe the UART output. When the MPLAB extensions are installed, MPLAB Data Visualizer is included, and we'll use that as our terminal window. Open the search bar inside of VS Code, type MPLAB Data Visualizer, and open it. Once MPLAB Data Visualizer opens, on the left side, we'll select the correct COM port for the Curiosity Nano, click on the cogwheel, and verify that the baud rate matches the value configured in the CirCom peripheral, which was 115200. Then, we can click Send to Terminal to begin streaming the data. Now, when we press and hold the capacitive touch button, the LED turns on and a touch detected message appears in the terminal window. When released, the LED turns off and a touch removed is printed. This confirms that the touch, GPIO, and UART are working together as expected. So with that completes part 2 of this video series. In the end, we've built and demonstrated a complete capacitive touch example using the peripheral touch controller and MCC inside of VS Code using the MPLAB extensions. If you'd like to follow along or modify the project, the full source code and hardware details are linked in the description below, as well as part 1 to this video series. Thanks for watching, and be sure to like, comment, and subscribe.